All right. Well, thank you all very much for showing up bright and early in the morning. I'm going to start with an introduction to uh, this topic of uh, language generation, which in some sense is a new topic, but in some sense is also a very, very old topic. Um, so, of course, there's a lot of excitement about large language models. I don't have to tell you to convince you. It's something that even my kids, who are like teenagers or just new teenagers, know about. Everyone knows about ChatGPT. Everyone uses it. The capabilities of these models have far exceeded our expectations and continue to amaze us. Uh, there's also been a lot of interest in language generation generally beyond. Yes. All right. Let me do that. Is that better? Okay. All right. So beyond all of the commercial excitement, the actual capabilities of these models that, there's none of you need convincing have really amazed everybody. There's been a lot of interest in the concept of language acquisition, and computer scientists and theorists in general have been fascinated by how humans acquire language and how machines might mimic this. And this is a topic that has been studied for a very long time. It goes back to seminal work by Shannon and Chomsky and so on. Um, I'm not going to talk about that aspect of language generation and that line of study, but I'm actually going to start with something much more modern, a very interesting paper from last year. I'm going to show you how the questions that this paper raises ties back to some very early work on language generation. So I'm referring to a very nice paper by Kleinberg and Mullyanathan from 2024. And they were taking sort of a theoretical look at language generation and asking the question, okay, if you want to think about this, the first thing we need to think about is what's the problem that these LLMs are solving? What is it? What's the problem statement? What do they do? Before we actually reason about the limitations and what's possible, what's not possible, trade-offs, and so on, we need to have a clear statement about what's the problem that they're solving. Okay, and you could sort of pontificate about this. One natural answer might be, well, what do these LLMs do? They take a large collection of text, and then somehow, using this large collection of text, they infer or they build a probability distribution over sequences of words, right? For every sequence of words, they assign probabilities. And then somehow they use this probability distribution to produce sequences of words. So they produce strings which have high assigned probability, and that's how an LLM works. And there's a whole bunch of other bells and whistles. You need to be able to respond to prompts and so on. But this is what LLMs do. Okay. But if you think about this, this is really what LLMs seem to do. But do we really need all of these details in the definition of the problem statement? Do we need probabilities, for example? You could say, in some sense, probabilities are convenient, but can we come up with a problem statement that's even cleaner than this, even more basic than this? And so here's an attempt to do that. And this was the problem statement that Kleinberg and Mullyanathan proposed. They said, well, what LLMs are trying to do is solve the following problem, right? Given strings from an unknown language, their goal is to produce valid, unseen strings from the same language. Okay, so the LLM is this black box. You give it a whole bunch of strings from some language. Eventually, the LLM figures out what that language is and starts to produce valid, unseen strings from this language. Okay, so I stripped out the probabilities, sort of extraneous to this problem statement. This is a much cleaner statement that maybe we can start thinking about and reasoning about. So a few things about this. By string, I just mean it's a sequence of symbols. It could be words in English, words in French. It could be C programs. What's a language? A language is a set of strings. It's the set of strings that I consider valid. So English language sentences, it could be haikus, as in the figure, it could be C programs or whatever, right? So this is the problem that large language models are trying to solve. This is the proposal, and we're going to play with this for a little bit and see how far we can get. So actually, this is very closely related to earlier work by Mark Gold. And I'll say more about this, but his paper was titled Language Identification in the Limit. And there's some differences between the questions that he was interested in and the question that Kleinberg and Mulyanathan asked. But let me just talk a little bit about Gold's work, because it's important and helpful in setting the context for what I'm about to describe. Okay, so Mark Gold was actually very interested in how humans, in fact, the littlest humans, babies, acquire language, right? They're exposed to language. Their parents and people around them, caregivers, are uttering strings of English or French or wherever they grow up, and by they pick up language and they start uttering sentences which initially don't make any sense, but then eventually become valid sentences in the language. So Mark Gold was actually interested in trying to understand what does it mean to be able to speak English, to sort of investigate theoretically how this could actually be achieved artificially by a computer program. Again, these are actually just sentences from his introduction. And he said, well, since we cannot actually write down explicitly the rules of English, any method to acquire language must somehow learn the rules implicitly from data. Right? So this was his motivation, and he was really thinking about a baby trying to pick up language from all of the inputs that the baby has, which is strings of valid sentences in English that are presented to the baby over time. Okay. I should say it'd be nice if this tutorial was interactive, so I do encourage you to stop me and ask questions. If you have any, happy to take any and all questions. Okay, so this was Mark Gold's work. In fact, it's remarkable that this work is actually about 60 years old now. So it's a really old sequence of papers. Gold's work was followed by important work by Dana Angloin about 12 years later. And I'll say a little bit about what Gold and Angloin did. But it's also interesting to note that Angloin was actually one of the founders of this conference, COLT. So it's indeed very nice that we are revisiting her work so many years after the work was done at COLT itself. Okay, so far we've described the language acquisition problem, language identification problem, but it's still not precise enough that we are able to reason about it or say anything meaningful about it. So let's try to make it even more precise. Okay, and for this we're going to take inspiration from the model that Gold proposed, and he proposed a game between adversary and an algorithm. Okay, so the adversary thinks of a target language K. And this target language comes from some set of allowed languages. Think about the target language as having some kind of finite description. There's a list of these finite descriptions. It's a countable list. For example, it could be all context-free grammars. So the adversary thinks of one of these languages, which has a finite description in this way. And then the adversary presents the algorithm with strings from this language. So the adversary is required to enumerate strings one by one. And this means that every string in the language must be presented at some point to the algorithm. It could be that some strings are repeated, that's fine, but eventually, every string must be presented. So for any one string in the language, there must be some time when the adversary presents it to the algorithm. Okay? And what's the algorithm doing? The algorithm is looking at these strings received as input and is guessing what the index of the language might be in this collection. Okay? And the goal of the algorithm is to hopefully guess an index I such that Li is indeed this unknown target language. Right? So that's the game that the adversary and the algorithm are playing. And what does it mean for the algorithm to succeed? Well, we'll say that the algorithm identifies the language K in the limit if there's some point beyond which all of the guesses of the algorithm are correct. Okay, so there's some point t star such that for all time steps t beyond t star, the guess of the algorithm is exactly the target language. Right? So is the setup clear? Yes.
So, like, just a question. So far, there's like very little difference with the standard path learning, right? So we do not utilize so far any structure of the things being like strings as opposed to like abstract elements, right?
Yeah, so the question is, are we actually using any properties of the structure of the language? No, we're not. We're just saying that the languages come from, in this case, a countable collection. Okay, so very, very general. We're not, for example, we've stripped out all of these probability distribution, no probability considerations, and so on. This is what we started out with, but then we kind of went down to this very clean formulation. So in some sense, it's a very general formulation. And you might even ask, okay, at this level of generality, can you even hope to do anything? We're not really exploiting very much about the structure of the language per se, right? Okay. Any other questions? Okay, I should mention a few things. One is, notice that the adversary has a lot of power. The adversary enumerates the strings of the language, and the adversary might withhold, important parts of the language or enumerate strings from the language so that certain parts of the language only get revealed much later. So in some sense, we're hoping that there's some point at which the algorithm succeeds, but this time for success could get delayed arbitrarily by the adversary. So invariably in such a model, this time t star that beyond which we succeed could be a function of the language that the adversary has in mind, but also on the enumeration order of the language that the adversary chooses. Okay, the adversary wields a lot of power in this model. Okay, all right, and that's fine. All we want is that eventually we'll succeed, right? And that's what it means to identify the language in the limit. Yes. The algorithm knows the enumeration. The algorithm receives the enumeration of the strings of the language one by one. So you don't know a priori what the enumeration order is, but you see the first string, and then you see the second string, and then you see the third string, and so on and so forth. Oh, yes, yes, yes. There is so when I say that it's a countable collection of languages, there's an agreed on enumeration of the languages that the algorithm has available to it, and it knows this is language 1, this is language 2, this is language 3, and so on and so forth. Yeah, so the question is this actually a restriction on the set of language families? So on one hand, we're saying that the set of languages is countable, but on the other hand, it's a fairly general class because any class where you have a finite description for every language is actually a countable collection. And if you think about most languages that you might be interested in, it's hard to think of a useful language family that's not countable. So it's a fairly general family. Okay? Yes?
So the adversary can enumerate strings in a way that it's impossible to distinguish between two languages. So for example, if there are two languages that only differ in finitely many strings, these are infinite languages, and if it only produces strings in the intersection.
Yeah, good question. So if there are two languages and they differ only in finitely many strings, is it possible that the adversary will actually prevent the algorithm from realizing it's one language or the other to distinguish between the two? Well, so long as there's one string that's different, right? Let's say one string belongs to language 2 but not in language 1. If the adversary is enumerating language 2, there must be some point in time when that particular string will be presented. So the adversary can delay satisfaction, but not forever.
Oh, so the languages are also countable. The language is also countable.
The language is also countable. The language consists of finite strings, so the language is, yes. So the language is countable, yes.
So T star is completely a function of the adversary and the language, and not
T P star is going to be a function of the language and the enumeration of the language chosen by the adversary. Yes, was that the question? Yeah, another question.
Meaning that every word of all languages appears at some point in the.
Yeah, so if the adversary has chosen a particular target language K, then for any word, any string, any element of that language, there must be some point of time when that element will be presented. Okay, so it's a very basic assumption. Yes.
I'm just curious, like, why was this like posed in an adversarial manner? Like, rather than you can ask this question, okay, how many set of strings I need to give so that it learns which language it is, rather than posing it as an adversary.
Well, I think in computer science we have this habit of trying to model our algorithms as playing a game against nature, which is modeled as an adversary, and we're saying no matter what the adversary does, no matter what challenges nature throws in our path, we will succeed. So that's why we think of it as an adversary. But yeah, you can ask all these kinds of questions, like how many inputs, how many strings do you need before you succeed, right? And right now I'm saying that my notion of success says I'm okay with just guaranteeing that eventually I will succeed, even if this eventually, the time at which I succeed is a function of the enumeration order of the language. Okay, all right, great. So these are great questions. They really help clarify the model. So so to recap, we have this game between the adversary and an algorithm. The adversary is presenting things of a language K, presents strings from K, and at each time our algorithm looks at the strings that have been presented and guesses what the index of the language might be. Okay. So a few things, and this was really motivated by Gould's motivation to study language acquisition in babies. So a few things about the model. One is the algorithm never sees negative examples. So we never see, no one tells us that, oh, here's a string that's not in the target language. We're only seeing positive examples. Okay. We're never told whether our guess is correct or not. We keep guessing, but no one actually tells us whether we've succeeded or not. And lastly, we can't actually ask whether a particular string is in the correct language or not. Okay, so we can't ask questions like that. All we do is we just guess. All right? So that's the model. So it feels like a fairly general model. And if you think that this model is too strong, too good to be true, in fact it is, and the main result that Gould proved about 60 years ago is that actually language identification in the limit in this model is impossible. Okay, and it's impossible even for very simple collections such as all regular languages. Okay, so if you're hoping for success, even with a simple setting, it's not possible in general. Okay. And 12 years later, Angluin in 1979 and also in later papers actually gave a precise characterization of which languages identification is actually possible for. And it turns out that it can be done, but in very, very restricted cases. Okay? Yes?
Would it be natural to change the assumption that every word in the language appears infinitely often? Because when you learn a language, you hear the word, you don't hear an apple just once.
The question is, would it make sense to modify the model so that every word in the language appears infinitely often?
And then would you change the
So yes, we can change the model to say that words can appear multiple times. I don't think it's actually going to change the impossibility result because in some sense we are worried that information not reinforced. We can always periodically go back and repeat strings that appeared in the past, and eventually every string will be seen an infinite number of times. So we can do that. It's actually not going to help us. In terms of this particular model, it actually doesn't really provide additional information to the algorithm. Okay. I mean, we'll actually see later in the talk, a simple example why identification is not possible. Okay, and hopefully we'll have time to cover that, and I'll convince you that this success in this particular model is not possible. Okay, so is this a dead end? Right. So we started with this question that Kleinberg and Mulyanatham asked, and actually let's go back and ask that question again. So they asked the question: given strings from an unknown language, we want to be able to produce valid unseen strings from the language. Okay, and Gold's result in Angloin's later characterization is basically saying that language identification is impossible. But there's a slight difference between identification and generation. Okay, if you could identify the language, then clearly you can generate. But maybe you can generate without identifying, right? So do you really? So does this negative result actually mean anything? So Kleinberg and Mulyanathan said, well, looks like generation is a weaker notion. For some reason, even though the identification question was resolved 60 years ago, nobody's actually asked about the generation question. So let's go ahead and investigate the generation question. Maybe we can characterize, what collections of languages generation is possible for. Okay. And this was the starting point. So they said, okay, let's now define a new game between the adversary and the algorithm. Same setup as before. The adversary thinks of a target language from a countable list. The adversary enumerates strings one by one. Let's say at time t, st is the set of strings that have been presented, have been enumerated so far. And each step, now the algorithm doesn't guess an index of a language, actually guesses a string. So guesses a string at, and the hope of the algorithm is that this string belongs to the target language. Okay, and of course, we don't get credit if we just repeat some strings that have been presented to us. So we only get credit if we produce a new string that belongs to target language but has not been presented to us so far. Okay, so we want our new strings to belong to k minus st. Okay, and success again means exactly the same thing. We succeed if there is some point t star such that for all times t beyond t star, our guesses are correct. Okay, so we guess valid strings that belong to the language that haven't been presented to the algorithm so far. Okay, so same question, I just tweaked a few things. So now this is the generation question. Okay, so now we have our language generation game. We're presented with strings, we guess a new string. Presented a new string, we guess a string, and so on and so forth. Again, we inherit all of the features that we had before, so we never see negative examples. We don't ever receive any feedback. And since we're requiring the algorithm to essentially produce new examples, we're just going to assume that all our languages are infinite. So there's always a collection of strings that we can draw from. It's not that we've seen everything, there's nothing to produce. Okay? All right. So back to the question. Language identification is impossible. What about language generation? Okay? And here, Kleinberg and Mulyanathan proved a pretty surprising result. What they said is that language generation in the limit is possible for any countable collection of languages. Right? So once you know Gold's result, it feels like maybe there's some limited collection for which generation is possible. It may be more general than the set of collections for which identification is possible. But no, in fact, this result is saying that for a very general situation, for any countable collection of languages, we can actually generate in the limit. Okay, this is a pretty surprising result. Okay? And again, just to drive the point home, what's the difference between generation and identification? Let's say you're trying to learn C programs, right? So after seeing many examples of C programs, if you're able to output valid C programs, we call that generation. Right? If on the other hand, if you're able to output a valid grammar for the C programming language, that would be identification. Okay? Identification is hard, but generation turns out is easy. Yes?
And in identification, the problem is that we can numerate sequences in some smart way, in such a way that will trick, or is it like random numerization also doesn't give you anything?
So the question is it that there is something in about the order in which things are enumerated? So in fact, I'll show you an example. I'll show you an example of a very simple family where we have a lower bound for identification. In that particular example, actually, we will enumerate things carefully. So the adversary will actually look at the algorithm and explicitly try to fool the algorithm. Okay, at least in the example that I'll show you. So you're saying if instead I change the problem and I say, oh, what if my strings were actually made available to me in some random order, or I don't allow the adversary power to enumerate, then does that change things? I don't think it should change things. It should still be hard. Off the top of my head, I can't come up with a very crisp reason why. Yes.
If there is a beneficial ordering where, I don't know, the first example for some reason involves the structure of a DFA using the interesting. I mean, if there is a collusion between the ordering and the learning algorithm, then I think that might be identified on it.
So the question is if there's collusion between the.
No, I'm saying that I think there is a collusion ordering of examples on the language that it reveals to the ordering like structural information about the outcome.
I see. So you're taking the question in another direction. You're saying if in fact the adversary was trying to help us, then the adversary might actually convey useful information in the sequence of examples that are provided that will help us eventually identify. Yes, that's certainly plausible. Yeah. Yeah, that's a good point. Yes.
Well, just to answer the question, if the adversary has to choose any distribution and then some from that distribution, that's basically the same as choosing any ordering. So you can also make it fail. Oh, if this distribution is such extreme gaps that you would force, essentially force it around.
Yeah. So.
The negative results still hold.
Okay, good point. So Nadi's point is that we could, if we're allowed to pick any distribution, then we can essentially pick a distribution that will basically give us this bad ordering that we wanted to produce. And so, allowing distributions doesn't actually help. Yeah.
So Angman has a paper in 1980 formalizing this idea and showing the distribution.
Okay, good. And it corrects me and says that actually there is a paper of Anglo in 1980 that actually formalizes exactly this thing. Yes?
The impossibility results for identification, does it change if no language is a sub-language of the other?
The impossibility results for identification, does it change if no language is a sub-language of the other? So off the top of my head, I don't quite remember, but in fact, the examples that I will give you, I'll give you a very simple example. There is this very nested structure actually in the examples. Okay. So, okay, all the questions are great. Let me take one last one and then I'll try to move on. Yes.
Threshold, because the question is is adversary universal or adversary knows probability results, or it knows the learner, whatever. For threshold, for example, learner suggests something and then adversary presents a bigger and bigger.
Yeah. So actually the adversary is going to inspect the code of the algorithm and say, I know the algorithm is going to do this, so I'm going to present an example that makes the algorithm look bad.
So it's not universal, it knows.
Yeah, that's the structure of the bounds that I'll present. Okay, so in the interest of trying to actually move on, these are great questions. I'm very, very happy that you guys are all very engaged. Let me try to show you some technical results beyond the statement of these things. Okay, so this is the theorem of Kleinberg and Mulyonathan. A few comments about the result. One is the algorithm only needs to generate from an infinite subset of K. Okay, so when I say it has to generate examples from the target language, new examples, it's not the case that you have to generate all of K. All I'm saying is just generate an infinite number of examples from K. It could be a really small subset. Okay, in fact, there's some tension in the algorithm, as you'll see, between validity, this requirement that you generate only valid strings beyond a certain point. That's a very strict requirement, right? And breadth, which is the desire that, ideally you should generate all of K. If you can't generate all of k, well, maybe generate a large subset of k, whatever that means, right? There's a trade-off between validity and breadth. If you enforce validity as a constraint, it's harder to get the breadth thing right. In fact, we'll talk a little bit more about this trade-off in the second part of this tutorial. And there are analogous notions. So you could think of validity as being the analog of hallucination, right? We're requiring that eventually our large language models do not hallucinate. And this notion of breadth is very intimately tied to what's called mode collapse, which is, if you really want to generate examples from a distribution, are you actually generating examples from a narrow portion of that distribution? Okay. All right. So let me talk about, let me try to convince you now why language identification is hard. And actually, the example is very simple. It consists of, so we talked about strings. Let me actually, in my examples, think of strings as encoded by integers. So in fact, my examples will consist of integers. My languages are just subsets of integers. Okay. Li is the language consisting of integers starting from minus I. So minus I plus 1, minus I plus 2, and so on and so forth. And L infinity is everything. Okay? All right, all the integers. Okay, so here's my lower bound. My algorithm is going to start by generating integers 0, 1, 2, 3, 4, and so on. Okay? At some point, my algorithm is going to say, okay, this looks like L0. In order for the algorithm to succeed, it's got to so let's say we have an algorithm that is capable of identifying correctly in the limit. Eventually, the algorithm at some point is going to say 0, 0, 0, 0, right? When the algorithm achieves that, we're going to say, aha, we're going to present minus 1, okay? And then continue producing positive integers, right? So at some point now the algorithm says, no, this is L1. So it's going to get this right at some point, right? When that happens, we're going to present minus 2. And then, continue producing positive integers. So each of these phases, the algorithm, if it's correct, will actually get L0 first. Then eventually it'll guess L1, eventually it'll guess L2, eventually it'll guess L3. The game will go on forever. And what have we done? We've actually enumerated L infinity. Right? What the adversary has actually done is enumerate L infinity, and the algorithm never gets it right. Yes? Yes, this is a universal adversary. We are actually looking at the code of the algorithm to determine when the correctness guarantee kicks in, and at that point we move on to the next phase every time. Yes, but the yeah, all right. So subtle difference, yes. Okay. So in fact, this diagonalization argument is something that we'll come back to in the second part of the tutorial. It'll show up again in Grigoris's presentation. Okay. All right. So notice that in this case, generation is actually simple, right? If you actually wanted to generate, you don't care about all these complications. You could just generate positive integers. Positive integers will belong to all of the languages that the adversary has in mind. Okay, so this suggests that perhaps maybe we should think of some kind of closure operation. Suppose we have a bunch of strings that we've received, st. Let's look at all the languages that contain st. Okay, so these are all the possible languages that the adversary could have in mind. Take their intersection. Maybe using that intersection is useful. Maybe we should output an element that belongs to the intersection minus the set of strings that we've seen so far. Okay, so it turns out that this doesn't quite work, and the problem is that this difference between the closure and the set st might actually be empty. Okay, I'm not going to go into details, but you can just take that previous example that we had and modify it a little bit to produce an example where the closure is exactly the set of strings that we've seen so far and nothing else. So in fact, using this closure is sort of a dead end. It is useful in some settings, this idea, which is why I mention it, but it's not useful in general. Okay, so this is a little bit of a dead end. Okay, here's another strategy that you might employ. You could say, Well, we have our languages. Let's, they're ordered. Let's use that order. Let's start with L1, and let's work with the hypothesis that L1 might be the right answer. And if we ever prove wrong, then we'll move on to L2. If we ever prove wrong, then we'll move on to L3, and move on to L4, and L5, L6, and so on and so forth. Okay, so here's a proof, actually, a wrong proof that this algorithm is correct. So, if our current language is not the target language, at some point in the enumeration, we will discover this, and we'll move on to the next one. So eventually, at some point, we'll reach the target language, wherever that is. And once we hit the target language, we'll never move on. So the algorithm is correct. Okay? This is a flaw. There's a reason why I said this is a wrong proof. And the reason why it's a wrong proof is that we could get stuck in a language which is a superset of the target language, right? There's nothing there's no information that we're going to get that's going to make us move on from our superset. Okay, so this is an interesting idea, but not quite correct.
What for the question asked earlier, right? Or languages are
Yes.
unchained to work.
Correct. Very good. So if you didn't have containment, then in fact, this strategy is correct, and you're right. It actually answers the question that was asked by the audience. Yes, very good. All right. So again, to illustrate what this issue is, here's a collection of languages. I've tried to depict them, pictorially by thinking them as these bar charts with filled-in entries corresponding to the words. And so I'll say that a language is consistent if it contains all the examples that have been presented so far. Let's say L6 here is the target language. We start with L1, then we move on to L2, and so on and so forth. And let's say this is the first word that's presented to us, then this is the second string that's presented to us, and so on and so forth. Okay? And so notice that this is the L6 here is the target language, okay? But L2 actually is a superset of L6. So we'll get stuck at L2 when we never move on, okay? And even if we move on from L2, L4 here contains even more things, right? And so we're never going to move on from L4, okay? All right, so here's another, let's modify the idea. Let's say a minimal consistent language is a language that is consistent such that there's no LJ that's also consistent, with LJ being a strict superset of Li, okay? Maybe we should try to find a minimal consistent language. And the trouble is that there may not be such a minimum consistent language. You could have an infinite chain of languages where each one is a subset of the other, and so on and so forth, and there's no minimal element. Okay? All right. Now that brings us to a final definition, which will actually lead to a correct algorithm. Okay, and that's the definition of a critical language. So I say that a language Ln is critical at step T if, number one, it's consistent, right? And number two, if any language before it is consistent, then Ln must be a subset of Li. Okay, so Ln is consistent. If there's some language before it that's also consistent, Li is consistent, then Li must be a superset of Ln. Okay, so if these conditions are satisfied, then Ln is critical, right? Okay, so here are a few important facts. A critical language always exists. Why? Just look at the lowest index consistent language. There must be a consistent language because the true language is consistent. Look at the lowest index consistent language, that must be critical. And number two, the target language will eventually become critical. Okay, and this is a key point, and let me try to illustrate that. So here is L6. Remember, L6 is the true language, right? Let's say we've seen these two strings at this point, and these are all the consistent languages, okay? But notice that L2 and here we have L3 and L5 are consistent, but L3 and L5 are not supersets of L6, okay? So L6 is not critical at this point. But why is L3 not a superset of L6? Well, there are some elements that are in L6 which are not contained in L3. At some point, we will see those elements. In fact, at the very next step, we see this element, which belongs to L6, but doesn't belong to L3 and L5. So L3 and L5 get knocked off the list of consistent languages. Every language that precedes L6, that's not a superset of L6, will eventually get knocked off the consistent list. And when that happens, for all these languages, L6 will indeed become critical. Okay? So here's the algorithm for generation in the limit. At step T, we're only going to consider languages L1 through LT. Okay? And we're going to say, let's look at the critical language LNT, which has the highest index amongst all the languages from L1 to LT. Generate from that language. That's the algorithm. Okay? Very simple algorithm. Why is this correct? I'm actually really out of time, but let me just tell you in a minute. I just explained to you that if you wait long enough, the target language will indeed become critical. And also you have this widening window of feasible languages, L1 to LT. So if you wait long enough, the target language LZ will belong to this window. Okay? When that happens, we will start being correct. Why is that? Because whatever the critical language LNT that we pick, that critical language, LZ is also a candidate critical language. We picked some language LNT. That language LNT might appear after LZ in our ordering, but this means that LNT is a strict subset of LZ. Okay? So everything that we generate will actually belong to the target language as well. Okay, and we're done. Right? So in this example, once we've seen these three strings, we've knocked off all the other languages. These are consistent at this point. L6 is critical, but so is L8, which appears later. So we'll start generating from L8, but L8 is actually a subset of L6, so we're correct. Okay? All right. So I'll stop here. That last part went by a little bit quickly, but I'll let you go back and think about how this notion of critical languages helps. One key point is that, as you see, the algorithm is designed to generate from a subset of the true language. We really exploit that. And this is this notion of mode collapse that I described. Anay and Grigoris in their presentations will have much more to say about this trade-off between validity and breadth, which will shed more light on that. This is a very simple model, but there are lots of additional features that we can add to it. And Chirag, who's going to speak next, is going to talk about stronger requirements that we can impose on the correctness guarantees. Okay, we talk about uniform and non-uniform generation. And finally, Charlotte is going to be the last speaker in the tutorial, in the second session. And she'll talk about additional constraints that we might hope for, diversity constraints, as well as dealing with noisy data. All right? Thank you for being such an engaged audience, and I'll turn it over to Chirag.